We now start the presentation for the second module of chapter 5. Recall that in the module 1 of chapter 5, what we did is that we have defined the Lebesgue integral of simple functions, and with the help of Lebesgue integral of simple functions, we have defined the Lebesgue integrability of bounded functions over sets of finite Lebesgue measure, just in the same way as we define the Riemann integral of bounded functions. In this module, we will see some basic properties of the Lebesgue integral of bounded functions and will make an important observation. So, we first go to the slide presentation now. So, we start with the same slide which we had presented as the last slide of module 1. So, this is the definition of Lebesgue integrability of a bounded function on a set E of finite Lebesgue measure, and we can prove the first result that for any bounded measurable function f from E to R plus, that is when integral E f d mu is equal to 0, if and only if f is equal to 0 almost everywhere on E. And now we can prove a very important theorem which states that a bounded function f defined on a measurable set E of finite Lebesgue measure is Lebesgue integrable if and only if it is measurable. Because recall that when we defined the Lebesgue integrability of a bounded function, we did not assume the function f to be measurable. So, the theorem in some sense states that for bounded functions, Lebesgue integrability coincides with the property of measurability when we consider the domain of the function as a set of finite Lebesgue measure. We start the proof. First, suppose that the function f is Lebesgue integrable on the set E. So, what does that mean? This means that the upper Lebesgue integral of f over E is equal to the lower integral of f over E, where again recall that the upper integral of f over E is equal to the infimum of all integrals t d mu, where t is a simple function greater or equal to f, and the lower integral is equal to supremum of integral s d mu, where s is a simple function which is less or equal to f. Since infimum and supremum of a set are the limit points of a set, and we are considering here sets of real numbers, we know that a point is a limit point of a set of real numbers if and only if there is a sequence in that set which converges to that limit. So, with this in mind, we can find for each k belonging to n two simple functions s k and t k, where s k is less or equal to f, less or equal to t k, and integral over E t k minus s k d mu, this value is less than 1 by k. So, we have for each k a simple function t k, and for each k a simple function s k. So, I have a sequence of simple functions t k and a sequence of simple functions s k. We take the infimum of all these functions t k and name it as t, and we take the supremum of all the simple functions s k and name it as s. Of course, since each t k or s k are measurable, and we know that for a sequence of measurable functions, its infimum or supremum function is also measurable. So, s and t are both measurable functions. Obviously, s and t are also bounded, and the functions s, f and t have this property that s less or equal to f less or equal to t. Subsequently, what happens is that if we consider the integral of the function t minus s, again see that both t and s are bounded measurable functions. So, t minus is again a bounded measurable function. Also, t minus s is non-negative. So, integral over e t minus s d mu, this is less or equal to integral over e t k minus s k d mu. This is again less than 1 over k, but this is true for all k belonging to n. So, if we increase the value of k, the right hand side tends to 0, but as t minus s is always greater or equal to 0. So, the value of the integral t minus s cannot be negative. So, we have this conclusion that integral over e t minus s d mu should be equal to 0. But recall that we have just seen a result that if f is a non-negative bounded measurable function and integral of f over a set of finite measure is 0, this means that the function is equal to 0 almost everywhere. So, applying that result lemma 1, we can conclude that the functions s and t are equal almost everywhere. But since f is between s and t, so we must have s equal to f equal to t almost everywhere. Again recall that we had proved if f is measurable and f is equal to a function g almost everywhere, then g also becomes measurable. So, here since the functions s and t are measurable, so the function f also must be measurable. So, this completes the proof of one part of our assertion. We will now go to the next part. Cut. ওখানে গিয়ে বসে বলি. Conversely, now suppose that f is a bounded measurable function defined on a set of finite Lebesgue measure. Next point, since f is bounded, so the set f is a bounded set of real numbers, and we can get closed interval a b such that Fe is subset of closed interval a b. Now, consider a partition P of the interval a minus 1 to b. Now, see that we have extended the interval on the left hand side. You will clearly understand why we have done that in the next slide. So, the partition P is chosen in such a way that its norm is less than epsilon by 2 mu e. Recall that what is the norm of a partition? The norm of a partition is the length of the largest subinterval of that partition. Define the set E R as collection of all x belonging to E for which L R minus 1 is less than f x less or equal to L R for r is equal to 1 to n. And here see that we have taken L 0 less than f x if we consider the set E 1. That is why we had taken the partition of the interval a minus 1 to b. Since the function f is measurable, obviously all of the sets E r are measurable because they are also inverse images of an interval under a measurable function, and above all E I intersection E j is equal to phi when I is not equal to j. So, they are pairwise disjoint. Further, the union of all these sets E r is equal to the set E. Now, construct two simple functions s and t in this way. Take the value of s as L r minus 1 for all x belonging to the set E r, and t is a simple function which takes the value L r for x belonging to E r. So, we take the interval L r minus 1 to L r open on the left hand side and closed on the right hand side. S x is a simple function which takes the left endpoint of each interval L r minus 1 to L r, and t is a simple function which takes the right endpoint, that is L r, on each subinterval L r minus 1 to L r. Clearly, the functions s and t have this property that s is less or equal to f, less or equal to t, and if we consider the integral of t minus s d mu over E, this is less or equal to sigma r is equal to 1 to n L r minus L r minus 1 into mu E r. This follows from the definition of Lebesgue integral of simple functions only, which is less than epsilon by 2 mu e, because recall that the norm of the partition is less than epsilon by 2 mu e. So, every difference L r minus L r minus 1 is less than this particular number epsilon by 2 mu e. So, the sum is less than epsilon by 2 mu e into sigma r is equal to 1 to n mu E r. But the sets E r are mutually disjoint, measurable, and their union is E. So, again using the additivity of Lebesgue measure, we get the sum is equal to mu e. So, we have epsilon by 2 mu e into mu e. So, this turns out as just epsilon by 2. But then we must have infimum of all integral t d mu over e, where t is a simple function and t is greater or equal to f. This should be equal to supremum integral over E s d mu, where s is a simple function, s less or equal to f, and from the definition of Lebesgue integrability of a bounded function, we now know that f must be Lebesgue integrable on E. So, in the second module of chapter 5, we had made a very important observation that for a bounded function f defined on a set of finite Lebesgue measure, Lebesgue integrability is equivalent to measurability. We now finish this module.